Deep ripping sandy soils is gaining popularity with Mallee farmers who are seeing big yield benefits from this practice. Mallee Sustainable Farming, with funding from the South Australian Grain Industry Trust, are investigating methods to improve the deep ripping process through a new project titled Deep Ripping to Enhance Production on Mallee Sandy Soils. In this video, Dr. Chris Saunders from the University of South Australia discusses the outcomes of a collaborative research project to investigate the working depth and tine design on soil loosening during the deep ripping process of Mallee sands.
So in choosing to set up our ripper, we need to decide first of all how deep we're going to work. So we'll know where our constraint is, and then we'll choose a tine suitable to get to that required depth. So here we have a standard straight leg ripper tine. Pretty conventional. What we have at the bottom here is the foot or the point, and this is designed to do most of the soil loosening and soil lifting. This is a shorter ripper tine, so this would work to about 450 millimeters deep. If we need to go deeper, then we would choose to have a deeper tine. So if we know our soil constraint is deeper in the soil profile, then we need to go deeper, so we need to choose a longer tine. Here's an example of a longer ripper tine. Again, a straight leg shank with a foot here to do the lifting and the braking. So when we're considering the setup of our ripper, we've obviously got to consider the depth we need to rip to, so the length of the tine, but we also need to consider the spacing of the tines. So as the soil breaks out from the tip of the tine here, then we know that it's going to loosen to the surface. So we can decide to change the spacing of these tines to suit how much breakout and how much soil loosening actually occurs when we're doing a ripping process. And on most rippers, that would be done by just adjusting the brackets here on the toolbar and bringing the tines closer together or moving them further apart.
The research looked at the soil loosening ability of deep ripping tines working in Mallee sandy soils at depths of 400 millimetres and 600 millimetres. After the ripping operation, soil pits were excavated and digital imaging used to quantify the cross-sectional area of the loosened profile. Draft forces were also measured using a Remick pull meter towed between two tractors during the deep ripping operation.
Here we have a representation of the soil loosened area of two different ripping depths. The first one here we can see was a ripping tine set to 400 millimetres deep, and this is the loosened profile that we measured in the field trials. If we look beside of it, here's the soil loosened area for a tine working at 600 millimetres deep. As you can see, the increased loosened area due to the depth. Obviously, the deeper we work the ripper tine, the more force it's going to take, but obviously that's related to what constraint depth we're trying to overcome.
The research project also investigated the effect of adding wings to a tine. A wing was fitted just above and just behind the main tip of the tine. The aim of the wing is to continue the soil lift that starts at the tip of the tine and to increase the width of loosening. These wings were custom made, as wings are not a common attachment found on deep ripping tines in Australia.
Here we can see the loosened area profile of a tine working at 400 millimetres deep with wings fitted. If we overlay these two profiles, we can see the difference in the loosened area. So the white profile is our tine working at 400 millimetres deep with no wings. And then when we added wings to the tine, we can see the red area is the area loosened with that tine with wings. We can see we have an increased distance of loosening to the surface and an overall increased area of soil loosening in the profile. Here in red, we can see the loosened area of soil with a tine working at 600 millimetres deep that had wings fitted. If we overlay these profiles, it's clear to see the increase in loosened area. The white one is our tine working at 600 millimetres deep without any wings. When we added wings to the tine, working at the same depth, we can see we have an increased loosened area of soil. If we then consider the soil loosening across the width of the machine with multi-tines, here we can see an example of a ripper set up on a 600 millimetre tine spacing, working at 400 millimetres deep. As you can see, the soil loosening doesn't quite interact here in the centre. We have a large area of unloosened soil between the tines. If we add wings to that ripper tine, working at 400 millimetres deep, we can see here by the loosened area that we have now a large interaction between tines. So given this increased interaction between these tines working with wings on, this may enable us to increase our tine spacing on the machine from 600 to say 800 and still achieve loosening to the surface on the interrow of those tines. So when we consider a tine working at 600 millimeters deep without a wing, here we can see the loosened area profile of that tine. If on the ripper we have those tines spaced at 600 millimeters, the tine working here in this one, tine working here on this one, we can see that the interaction between those two tines is pretty minimal, with a large undisturbed area here between the tines. We've just about achieved soil loosening to the surface with both tines, but very minimal interaction between the tines. So when we consider the same tine spacing on the ripper of 600 millimeters, but with a tine with wings fitted, you can see due to that increase in soil loosened area, we have a large interaction of loosened soil here between the tines. We have a smaller area of undisturbed soil here between the tines. So what this may enable us to do is actually increase the tine spacing on our ripper, say from 600 to 800, and still achieve soil loosening to the surface between those two tines. Obviously, by adding wings to a tine, we have a trade-off. We increase the force, but we also increase the loosen area. So in the field trials that we conducted, we found there was a 24% increase in draft force by adding wings to a tine at 600 millimeters deep, working at 4.5 kilometers an hour. But from the profiles we measured, we found there was actually a 50% increase in soil loosened area. So therefore, we have a better benefit in soil loosening than we do have penalty in draft force. The next steps of this research will be to consider the crop response from this ripping. Do we need to loosen the soil all the way to the interrow, or are we able to increase our spacing and reduce the number of tines on a ripper and still get the crop responses that we are achieving by loosening that constrained soil profile?